Okay, so we are discussing the prime number theorem One way of stating, as we have learned in previous classes, is that the partial sums of the von Mangold function are asymptotic to x as x goes to infinity. And we are actually going to prove a stronger version of the prime number theorem, that is, we prove an estimate with effective error terms. So far what have we learned? We learned the Perron's formula, which teaches us how to express this partial sum in terms of a contour integral. This is an extremely important technique in analytic number theory with applications to probabilistic number theory as well, because at the end of the day it is teaching us a technique to evaluate or to understand the value distribution of appropriate arithmetic functions. So what does this formula say? It says that the sum of these von Mangold function is equal to 1 over 2 pi I times integral c minus it to c plus it, where c and t can be chosen appropriately, of the Dirichlet series which generates these arithmetic functions, and that is minus zeta prime of s over zeta of s, x raised to the s over s ds, plus an error term which is O of summation n going from 1 to infinity. It is an infinite sum, but it will converge for appropriate choices of our parameters. So lambda of n x over n raised to the c times 1 over t absolute of log x over n, the error term, and this holds basically for any, what are the restrictions on c and t? So t is something positive, c is also something positive, but with the restriction that, in fact, we want this series to be absolutely convergent for real part of s equal to c. So given the series that we have, we want c to be something greater than 1. It could be something very close to 1, but it has to be greater than 1. And in our previous class, we saw how to make appropriate choices of c which are really close to 1, but which lead to rectangular contours which will not contain any points of singularity of these Dirichlet series under consideration. So we learnt also last time, let's recall that our focus was primarily on the contour integral, and we saw that if you choose t to be something which is greater than or equal to 2, you choose b to be equal to 1 minus a1 prime, where a1 prime is some absolute constant appropriately chosen, as we had done last time. If you choose b in this way, and if you choose c to be equal to 1 plus a1 prime over log t raised to the 9, then we learnt last time that our contour integral 1 over 2 pi I with the choices of c and t as given above, minus zeta prime of s over zeta of s times x raised to the s over s ds turns out to be equal to x plus an error term x raised to the c over t plus another error term x raised to the b times log t raised to the 10. Now notice b is strictly less than 1, although it is quite close to 1 as t becomes very large, but it is strictly less than 1. So we have to choose capital T in such a way that x to the b times log t raised to the n would be strictly less than the order of x, at the same time ensuring that this term itself does not become very big. Okay, because you see over here x raised to the, you have x raised to the c is something greater than 1. So in the denominator you must have something that will remove enough of the order of, enough of the power of x to make sure that the term has order strictly less than the order of x. So we have to choose our t carefully. More about this soon, but this is as far as we got last time. And today we want to focus on this error term and combine whatever we get to derive an effective version of the prime number theorem, which of course leads to the prime number theorem itself. So here is our theorem, first theorem that we proved today. So now notice, when you have partial sums of lambda of n running up to x, whether you take the greatest integer of x or something which is bigger than greatest integer but not as big as the next integer, you will have the same sum. So what we do is, we will choose our x's carefully in such a way that the evaluation of the integral and the error term becomes feasible, but at the same time it does not affect the quality of the theorem that we are trying to prove. So let us do the following. Let us take x to be some natural number plus a half, alright, and whatever we prove, whatever asymptotics we get will actually apply to any x, but the method that we are going to use to prove our asymptotics will work better with such choices of x. So let x be as mentioned here with c and t as above, as I mentioned here. So capital T is something greater than or equal to 2 and c is something that is a little bit shifted to the right of 1, but which becomes smaller and smaller, closer and closer to 1 as capital T becomes very, very large. So with such choices of c and t, our claim is that the error term x raised to the c over t summation n going from 1 to infinity lambda of n, okay, over n raised to the c times 1 over absolute log of x over n. This error term is bounded above by x raised to the c over t times log t raised to the 9 plus x log x whole square over capital T. These are the two terms which will show up in the error estimate. So let us prove this. Before we prove this, just remember, in order to prove the prime number theorem, we will have to combine this as well as this and see what is the optimal choice of capital T to make the whole thing give us the prime number theorem. Anyways, let's start with proving this theorem first. So let us look at this sum carefully. Suppose we break this term into two parts. We have this infinite sum. So the first thing, so I'm just going to start with this remark. Suppose I start with breaking down the sum into n less than x and n greater than x. Then what happens? You see, we have to be very careful about this term log of x over n, which is in the denominator. We need a lower bound for this term so that we will have an upper bound for 1 over this. If your lower bound, the best you can do is 0, if all you can say is that this is something non-negative, that is not good enough for us, because we would like to give a very specific positive lower bound so that you can have a positive upper bound for this term with this in the denominator. Okay, now what happens when you have n is less than x? You are choosing x in n plus a half. So x is of the form a plus a half. So if n runs all the way up till greatest integer of x, so n is going all the way up till a, right? So now what can you say about log of x over n? N is less than x, so absolute of log of x by n would be equal to log of x over n. So this will just become log of a plus a half is, so what you will have is, so over a. N is less than or equal to a, and so what you have is a bound of this form, which is log of 2a plus 1. So, or rather this is just 1 plus 1 over 2a, okay. If your a becomes very, very large, this bound is coming closer and closer to log 1, which is just 0. So, this kind of a division into two sums will not be very efficient. Rather, what we try to do is, we try to stop well before x, let's say some constant times x, where that constant is strictly less than 1, in such a way that the lower bound would be something that would have an absolutely positive lower bound. So what we do is, instead of going up to just x, we take n less than x over 2. This is just a division that works. You could try other types of partitioning as well. Then we take n greater than 3x by 2. By the way, if you were taking n greater than x with a similar kind of reasoning that we just saw, you will see that. So, of course, now your absolute of log of x by n would be equal to log of n over x, and you will see that as your x becomes very, very large, this is coming dangerously close to 0, which is not what we want. We would like an absolute positive lower bound. So, we break this into n less than x by 2, n greater than 3x by 2, and whatever lies in between, with a chunk of the work would have to be done, a good chunk of the work would have to be done for these terms, because this is where, this is the region, this is the interval where n is coming, n has the possibility of coming very close to x. So, we have to be careful about how we bound this sum in this regime here, okay. These two are fairly simple to evaluate, and we do just that. So, notice, if n is less than x by 2, then what do you know? You see that absolute of log of x by n is equal to log of n by x right. Sorry, not log of n, just log of x over n. Since x is strictly greater than n, you are taking n to be much lesser than x, in fact less than x over 2. So log of x by n is greater than log 2. Okay. Similarly, if you take n to be strictly greater than 3x over 2, then absolute of log of x over n is equal to log of n by x, but n is greater than 3x over 2. So log of n over x would have to be strictly greater than log of 3 over 2. This is good. We've got absolute positive bounds, lower bounds for absolute of log of x by n. And so now suppose I write out n less than x by 2 of this error term here, plus the other term n greater than 3x over 2 x raised to the c over capital T lambda of n over n raised to the c 1 over absolute log of x by n. When you combine these, what happens? This is certainly less than x raised to the c over capital T, and in both these regimes 1 over absolute of log of x by n is bounded above by 1 over log of 3 halves. Right? So in fact this is a very specific constant. It will get absorbed in the O estimate, but let's write it for now. And then what are you left with? N greater than x by 2 lambda of n over n to the c plus n greater than 3x over 2 lambda of n over n raised to the c. So what do you have? This is certainly less than, these are non-negative terms, so okay, which is, so certainly this term is x raised to the c over 2, and this is minus zeta prime c over zeta of c. And what do you see? This is less than x raised to the c over t. We learned last time that if you've got some numbers s here for which your the real part lies in certain region and imaginary part lies in a certain region, then you've got suitable bounds. And so from what we learnt last time, a bound for this value for s equal to c exactly, where c is something slightly to the right of 1, turns out to be 1 over absolute c minus 1. All right. And what was our choice of c? C was something 1 plus a1 prime over log t raised to the 9. So c minus 1 is a1 prime over log t raised to the 9. So 1 over absolute of c minus 1 just becomes, it gives you a contribution of a power of log t in the numerator over capital T. Okay. So this takes care of the tails. Now let's focus on this part here. Now since your n's could come very, very close to x, this kind of a straightforward bound does not work, but with a little bit of thought you see that this is not too difficult either. So what happens now is that in the case when x by 2 is less than n, which in turn is strictly less than 3x over 2, if n lies in this regime, then what we do is we do the following. Make the substitution z is equal to 1 minus n over x. And if n lies in the region where we say it does, then you can verify that your absolute of z would be strictly greater than 0 and strictly less than a half. I will leave it to you to verify this. And therefore, now what you have is, you see, log of x over n just turns out to be exactly equal to minus of log of 1 minus z. Okay, and this of course if your absolute z lies between 0 and half, this has a Taylor series expansion which is just summation k going from 0 to infinity, actually k going from 1 to infinity, z raised to the k over k. And so what you get finally is that you can take minus of log of 1 minus z over z. Use the Taylor series expansion and taking different cases, one is when z is negative, the other when z is positive, but in both cases the absolute z is bounded above by a half. You can take two different cases, expand the Taylor series and apply appropriate inequalities to derive that this is in fact, you can actually find a positive constant, let us say m, so that absolute of this would be greater than or equal to m. In other words, what you are saying is that this is again, I leave this verification as a very standard exercise for you. And so this tells you that you can now apply this to your absolute of log of x over n. Okay, it will turn out to be have a lower bound of the form which is absolute of, you see you are saying absolute of minus log of 1 minus z is greater than absolute of z. So, you just apply that. What is absolute of z? It is 1 minus n over x, which is absolute of x minus n over x. And therefore, in this part of the sum, we use this lower bound for absolute of log of x by n. Thus, x by 2 less than n less than 3x over 2 of the sum that you are after, lambda of n over n raised to the c times x raised to the c over t 1 over absolute of log of x over n turns out to be less than. So, first of all, lambda of n, you know that it picks up the value log p if n is a prime power, okay, and 0 otherwise. Now, if n is a prime power bounded above by some constant times x, then you can also show that lambda of n would be at most log of x. So, we can take this log of x out. Then notice that x over n, in the way we have written this inequality, x over n is at most bounded above by 2. So, you can take x by n raised to the c outside and write it as something that is bounded above by 2 raised to the c. And you have, of course, over capital T times summation n running between x by 2 and 3x over 2, 1 over absolute of log of x by n is bounded above by x over absolute of x minus n. So, you can again take x out and you have 1 over, you have reduced this whole sum to essentially calculating this part, which does not look too hard. Now, notice one thing, c is something which is greater than 1, but very, very close to 1. So, it is obviously less than 2. 2 raised to the c therefore has to be strictly less than 4, which is an absolute constant. So, you can actually just absorb this in the less than term. So, x times log x over capital T times the sum above. Remember, we have started off with x to be something which is a natural number plus a half. Let us say x is a plus a half, or the greatest integer of x plus a half. Then you can verify that if n lies between x by 2 and 3x by 2 as we need, and x is of the form greatest integer of x plus a half, then your absolute of x minus n, okay, obviously it will be of the form some integer plus a half, but with some thought you can see, because of the bounds that are given to you, absolute of x minus n lies in half, 3 by 2 and so on, all the way till x by 2 plus a half. I will let you verify this, very straightforward verification given the bounds on n. And so, this tells you that of the sum of the terms that you are after in this regime, x by 2 less than x less than 3x by 2 is less than x log x over t into, what do you have? Your n runs from, rather your k runs from 0 to half of the greatest integer of x. Okay, if the greatest integer is even, then this is an integer. If it is not, then it has to stop to the left of that. And what are your terms? 1 over k plus half. This sum here is certainly contained or less than or equal to the sum that I mentioned here. And notice, this is what you have 2 times 2 over 2k plus 1, where k runs from 0 up to some constant times x, right, which looks, you have seen that sums of these forms are bounded above by some multiple of log of x. Okay, so this whole thing is just O of log x, and therefore what you end up getting is x times log x whole square over capital T. Okay. And so, combining what we had for n less than x by 2 and n greater than 3x by 2 along with what we have for n lying between these, what we have is we have to combine this error term here with what we obtain here, and thus summation n going from 1 to infinity lambda of n x by n raised to the c 1 over capital T absolute of log x by n is less than x raised to the c over t times log t raised to the 9 plus x log x whole square over capital T. And combining this with the estimate coming from the contour integral part of the partial sums of the von Mangold function, we conclude the following. Therefore, summation of lambda of n as n runs up to x is equal to x plus O of x raised to the c log t raised to the 9 over t plus O of x log x whole square over capital T plus O of x raised to the c over capital T, which was coming from the error terms in the contour integral, but that error term gets absorbed in this. So, you are just left with O of x raised to the b times log t raised to the 10. Okay, now we have to see how to make an appropriate choice of capital C, which will give us a non-trivial error term. By non-trivial, I mean that it has to be of order less than the main term. So, let's just focus on the error term. Among x to the c, x and x to the b, let us choose that power which is the smallest and pull it up. Okay. So, I take x raised to the b. Okay. Then I also take the smallest power of log t lying in these terms. So, let me just take log t raised to the 9 out, and let us see what we are left with. I am only focusing on the error terms. So, what do we have? We have first of all x raised to the c, but what was c? C minus b. So, b was 1 minus something, c was 1 plus something, those somethings were the same, and so based on our choice of b and c that we had made above, what we end up getting is x raised to the 2a1 prime over log t raised to the 9. Okay, x raised to the this power over capital T. What about the other terms? So, you have x times log x whole square over t. Okay, what happens to that term? So, that will just become x raised to the 1 minus b, since you are pulling out x to the b. Okay, there is an extra log t raised to the 9. So, what you have is log x whole square over capital T okay, times log t raised to the 9 in the denominator, but since this is in the denominator, we can certainly bound this by log x square over t, okay, plus what are you left with in the last bit? Just log of t, okay. So let's understand the contribution from each of these parts. So what happens now? What is this less than or equal to? So basically, note the following. So you have x raised to the 1 minus b here, all right, and you had over here, you had x raised to the c minus b, which is what turned out to be 2a1 prime over log t raised to the 9. C minus b is certainly greater than 1 minus b. So this term seems to dominate this. There is a t in the denominator here also. What's more, now you know that log, what is one of the things we've learnt about the growth of logarithm? It is less than x raised to the theta for any theta greater than 0 or for any epsilon greater than 0. And so x raised to the 1 minus b times something which is bounded above by any arbitrarily small power of x would certainly get absorbed in the error term x raised to the c minus b, since c is something greater than 1. And so what you have is less than x raised to the b times log t raised to the 9 times, we can ignore this error term now since it is of order which is less than this error term. So you have x raised to the 2a1 prime over log t raised to the 9, okay, over capital T plus log t. So we have to be careful. If t is too small, then this will become very big. If t is very big, then this becomes very big. So how do we combine the two? So what we now do is we choose t in such a way such that 2a1 prime times log x is equal to log t raised to the 10. Why are we choosing it in this way? I have tried out many different choices and this seems to work the best. Why does it work? Okay, with this choice, what happens is, so a few things happen. First of all, 2a1 prime over log t raised to the 9 turns out to be equal to log t over log x. Okay. Also, we observe that your log t itself turns out to be equal to 1/10 of this term here, 2a1 prime log x. So roughly speaking, we are going to choose t in such a way such that log t is approximately 1/10 of log x. How does this help us? This choice of t makes our error term work. So what we have is, so our error term becomes, what is it? So you have x raised to the b times log t raised to the 10. Okay, so let me just write this down. Yeah, x raised to the b raised to the 9 times what happens to x raised to the 2a1 prime over log t raised to the 9. Okay, so it tells you that this equality tells you that x raised to the x raised to this quantity will just give you t itself, and then there is a t in the denominator. So you have t over t plus you just have log t, right? So this term is just giving you something which is O of 1 and you have O of log t. So what do you get? This gives you an error term x raised to the b times log t raised to the, okay. But what is this log t? We have expressed this in terms of our log of x. It is something like 1/10 power of log of x. So we now put that into this consideration to check at most what is this error term. Remember, b involves the variable t as well. So now finally what we observe is the following. Observe. Suppose I write log t over 2 minus log x, where log t is of the form 1/10 of some constant multiple of log x. So basically something which is O of log of x raised to the 1/10. Subtracting log x from it will not make a very big difference because log x grows at a rate which is much smaller than any power of log x. This is one of the most fundamental properties about the logarithm function that we have studied. So if I were to take some power of my logarithm of x times, so let me just take 1 over 11th, which is just a wee bit smaller than 1/10th. Basically, we can take 1/10th minus epsilon for any epsilon, but let's be specific and take log x raised to the 1/11th. Because on the right hand side you have log x raised to the 1/10th, something to the order of log x raised to the 1/10th, you know that this is certainly true. And therefore, what this means is that now if you take exponentials, or okay, don't take exponentials right now. Since we are doing these estimates for the first time, let's work out all the details. D prime, so some constant, you can find some absolute constant d prime, so that d prime times log x raised to the 1/11 is less than log of, what do you have? You have log of capital T over 2. Looking at how you've chosen t, what you will end up getting is that this is less than log of x raised to the log t over 2 log x, okay, over log x. And so because of this, we end up getting thus e raised to the d prime times log x (1 raised to the 11) is certainly less than, I am just taking exponentials of both sides. So, x raised to the log t over 2 log x over log x. Okay? And what does this tell you? That thus your log x, just take the reciprocals, over x raised to the log t over 2 log x t, this thing is less than e raised to the minus d prime of (1 over 11). And combining all of this together, that what do we get? Thus, the error term that we had, O of x raised to the b log t raised to the 10, okay, will turn out to be less than your x. So, x to the b over log t raised to the 10 will just be, it will involve this term, and so what you end up getting from this inequality over here is that this error term finally turns out to be, so this is exactly equal to, or let me put, this is less than x over x raised to the log t over 2 log x times log x, okay. So, x over something which is bounded above by this, and so this is less than x over e raised to the d prime of log x raised to the 1 over 11. Okay. So, to put it all together, let us see. This has basically given us an error term in the prime number theorem. So, we get, what do we get? Our sum of lambda of n is x plus O of x over an exponential of log x. Now, let us spend some time on understanding the nature of different types of error estimates. What does this, if this looks like Greek and Latin to you, what does this actually mean? Why is this little o of x? So, remember, always remember, this is the fundamental inequality at the heart of everything. Log of x is less than x raised to the epsilon, okay, for any epsilon greater than 0. In particular, if epsilon is something very close to 0, but positive, this bound will work. Okay. So, what does that mean? What this means is that, suppose I take d prime. Let us compare, let us take some x raised to the theta, okay, where theta is less than 1, and let us take e raised to the minus some d or d prime as we took here, log x. So, e raised to the minus d times some really tiny power of log x, where, so let's start with kappa to be something positive, okay. Now, our claim is that from the fundamental inequality of the logarithm, it turns out that if 0 is less than kappa is less than 1, then x raised to the theta, okay, would be of a much smaller order than okay. Why is this so? Sorry, not this would be, let's just compare. So, d of log x. So, if kappa is something less than 1, then log x raised to the kappa would be would be much smaller than log x, right. So, this would be less than 1 minus theta of log x. Theta is something that you have started off with, it is less than 1, 1 minus theta is a positive quantity. This inequality will definitely hold provided kappa is less than 1. What does that mean? That means that d times log x raised to the kappa is less than log of x, so raised to the 1 minus theta. And so, this what this ends up giving you is that this is less than if you take the exponentials, what you end up getting is that this is less than x raised to the 1 minus theta, okay, which is of course just x over x raised to the theta. And therefore, what this tells you is that your x raised to the theta, just bring this to the left hand side and bring e to the d log x raised to the kappa to the right hand side, it will go in the denominator. It is certainly less than x over e raised to the d times log x raised to the kappa for any kappa which is strictly less than 1. Okay. So, this kind of an error term, x raised to the theta, very explicit power of x which is less than 1, would be of better quality than this error term here that we seem to have obtained in the prime number theorem. On the other hand, how does this error term behave with respect to x over any arbitrary power of log x? Okay, so observe the following. Compare x over e raised to the d log x raised to the kappa, okay, where d is some positive constant. Compare this with x over log x raised to the a, where a is greater than 0, positive, and it could be arbitrarily large. Okay, log x raised to the any large power, 100, 1000, 1 millionth. Okay, how do these two compare? Notice the following. Your d prime log x, d log x raised to the kappa, where kappa is something positive, okay, although it is less than 1, it is still some positive power of log x. It will always be bigger, much bigger than a log of log x, because we just saw here that log of log x would grow much slower than any power of log x. So, this is what we are saying here, log of log x is going to grow at a much smaller rate than any power of any positive power of log x, even if that power is very, very tiny. And therefore, this tells you that e raised to the d of log x raised to the kappa is bigger than what do you have? So, here this is log of log x raised to the a. So, this is bigger than log x raised to the a for any a, positive, arbitrarily large, right. So, exponential power of any small power of log x will grow much faster than any power of log x itself, and therefore, x over e raised to the d log x raised to the kappa is less than x over, actually little o, you know, but certainly this is also true. All right. So, if you are going to be comparing different types of error terms in the prime number theorem, I mean, what is the error term that you have and how does it compare to other functions? Okay. So, what we have is that x over e raised to the d prime of log x raised to the 1 over 11th is certainly of a much larger order than x raised to the theta, where theta is something less than 1. So, if you were to obtain an error term of the form O of x raised to the 3/4 or O of x raised to the half, that would be significantly better than the error term that you have with your existing methods. And in particular, as a corollary of what you have, because of what we just wrote here, that this is dominated by x over any power of log x, this arbitrarily large, okay, this is actually a consequence of the error term you have obtained here, but this dominates, this is bigger than this. So, to write this is a sharper, this is a sharper error term than just writing O of x over some power of log x. But the even better is to be able to say that the error term is O of x to the theta. So, we haven't quite yet reached here. If you assume the Riemann hypothesis, then you can actually get theta to be something which is little bit bigger than half. You can take x to the half plus epsilon, you will get that in the error term. But for that you have to make this very strong assumption of Riemann hypothesis. So far, unconditionally, just by the plain and simple method of contour integration, the error term that we have is this. And behavior, your information about behavior of zeros of the Riemann zeta function will help you to move, as I had mentioned in the last class, in the contour integration method based on what you know about the location of the zeros. You can determine how far to the left of real part s equal to 1 you can move your contour, and that eventually determines what power of x you are able to take. Okay. So, this is a short discussion on nature of error terms. This is the version of the prime number theorem that we have. From this we immediately deduce that as x goes to infinity, this error term will be little o of x, right, and therefore, as x goes to infinity, this sum is just asymptotic to x, and we have made some observations about the nature of this error term. What is it? I am comparing it to some other functions of x and trying to understand which is worse and which is better. All right. So, this concludes our discussion of the prime number theorem as an application of Perron's formula, and I will stop the class for today.